the last part for today. Let's put it all together. Okay, so each energy level is going to be subdivided into sub-levels, and we have 4 sub-levels, as we have been seeing: S, P, D, and F. Energy level 1, let me put it back up. Energy level 1 has only one sub-level, and its designation would be the S. So now we're filling out the second page of C14. We are in the middle of the second page of C14. Energy level 2 has 2 sublevels, and they're called S and P. Energy level 3 has 3 sublevels and are designated S, P, and D. And then energy level 4 has 4 sublevels and are designated S, B, D, and F. And then for the 5th one, we would include the G, but we are not going to be concerned about this one. Okay, so energy level 1 contains the S sublevel, and each sublevel can be subdivided into orbitals, and each orbital can hold 2 electrons. So let's talk about this. The S sublevel contains a maximum of 2 electrons. So if it has a maximum of 2 electrons, it only has 1 orbitals. But P contains a maximum of 6 electrons. If each orbital can hold 2 electrons, then it has 3 different orbitals. D sublevel can hold a maximum of 10 electrons. If each orbital can hold a maximum of 2, then it has 5 orbitals. And then the F sublevel can hold a maximum of 14 electrons, so it must have 7 orbitals. 2 electrons per each orbital, that's a maximum of 14 electrons, and it looks like this. This is how they look like. So let's take a look in more detail. The S orbital only has 1 orbital that can hold 2 electrons. So S is spherical shaped and can have a maximum of 2 electrons. In P orbitals, we have 3 because each of them can hold a maximum of 2 electrons, and they look like this. They look like a lobe shape. They are located against different axes: X, the Y, and the Z axis. So here we have 2 electrons, 2 electrons, 2 electrons for a maximum of 6 electrons. The d orbitals, we have 5 of them, because each of one, even though it looks like a petal like 4, this whole thing can only hold a maximum of 2 electrons. So 2 and 2 and 2 and 2 and 2 would be 10 electrons maximum, and they kind of look alike except for this one. They do not have to look the same. And then the F orbital looks like this. Each one of these, even though they look really complicated, can hold a maximum of 2 electrons. So we have 2, 4, 6, 8, 10, 12, and 14 electrons that it can hold. And we're going to start placing them in the alpha diagram. But first, let's go back to our analogy. what do the hugs represent, what do the floors represent, and what do the rooms represent. So for rule number 1 of the hugs, let's go back to C13. Hugs are lazy. So it means that the Aufbau principle says that electrons are going to enter the lowest energy level first. So we're going to start with the 1s, then the 2s, then the 2p, 3s, 3p, 4s, 3d, and so on. So we're going to start with the lowest energy first, and then we're going to go up, increasing in energy. For orbitals with the same energy level, S is less in energy than P, then D, and then F. The second one, if hogs are in the same room, they will face different directions. This is actually talking about Hund's rule. And Hund's rule says that electrons prefer to be unpaired in orbitals. Remember, electrons have the same charge. They're both negative. If they're close together, they're going to repel. So they prefer to be unpaired with equal energies. They only pair when they have to. So here we're going to start placing them according to the first rule in the lowest energy. But according to Hund's rule, we're going to place them with different spins. So one is going to be facing upwards, the one downwards like this. Now, just in rule number 3, in the hogs can sting each other unless they have to. There's a typo there. Hogs sting, so you can put more than 2 in a room. This is talking about Pauli's exclusion principle. An atomic orbital may describe at most 2 electrons of opposite spin. Let's just continue to fill this out. So here you would go into the opposite spin like this. So here, Hund's rule, electrons prefer to be unpaired in orbitals, just like I was doing here, unless they have to. So here, they will prefer to be unpaired unless they have to. Then this is actually going to go on your paper for the Hogs rules. That's the third one. Hogs can stand each other unless they have to, with the typo. This is Hund's rule. And here, Pauli's exclusion principle is talking about if dogs are in the same room, they will face different directions. So this is talking about an atomic orbital may describe amongst 2 electrons of opposite spin. So here's how we will place them. One facing like this, the other one like that. So here they are. Okay, I'm going to show you this video.
Now for carbon, we're going to first of all fill our 1s sublevel. And so we put 1 electron in to the 1s, and then we're going to add our second electron. And so remember that they're going to have opposite spins. Then next we move to our 2s, and we're going to put 2 electrons in our 2s, and they're going to have opposite spins. Next we have to add 2 more electrons, because remember there's a total of 6. So we're going to add 1 electron to our 2px sublevel, and we can't add another one here because remember, according to Hund's rule, we have to put 1 electron in each orbital of that sublevel. So what we have to do is put in another p orbital, and this is going to be our 2py orbital, and we're going to add one electron to that orbital. And remember that they're going to have the same spin in the same direction according to Hund's rule. And so now we are done. We've added a total of 6 electrons. So we're going to have 1s2, 2s2, and 2p2. But the 2 electrons in the p sublevel are going to be in 2 different orbitals and have the same spin.
Okay, now make your prediction for sodium and see if you can come up with the shape of how it will look like. Complete an energy diagram for hydrogen and write the electron configuration for hydrogen on the bottom. Then do it for the rest of them. Helium, go to the next page. You have lithium, boron, oxygen, and so on. So you're gonna try to do it by yourself and then work with someone to check your work and then check it with someone else, and I will check it whenever I come back. Okay, let's just recap what we have learned so far. What's an electron configuration? Well, it is the notation that shows where electrons are located in an atom. Just like in the YouTube video that we watched, we're gonna start placing electrons in different. We're not following Bohr's model anymore. We're following the quantum model now, and we're predicting where electrons can be located by all these different orbitals. So it's just like giving an address for the electrons. What's an Aufbau diagram? It is the diagram, just like the hotel, to show the location and energy of electrons in the atom. We use it to help us know the electron configuration of an atom. And why do we use it? To figure out the electron configuration and in demonstrating the 3 main principles. So here we can explain it with the Aufbau diagram. We're always filling in our Aufbau diagram in this order. Here 1s, 2s, 2p, 3s, 3p, 4s, 1 lower, 3d, 4p we continue, 4s, 1 lower, and then we continue with the 5p, 6s, 1 lower, and then we continue with the 6p, 7s, and then here between the 6s we will actually go to the 4f and then 5d, 6p. Remember, these two actually go right here. So whenever we get into 7s, we go into 5f, then 6d, and then we continue and so on. How does the orbital notation work? First, we identify how many electrons an element has. Once we know the number of electrons, we fill in the Aufbau diagram according to the 3 main principles, just like the hogs in the hotel. And then we write out the electron configuration in order of increasing energy. We use the exponents to tell how many electrons are in that orbital. And I think this is it. Yes, this is it. Finish up to page 7. Page 7 of C14, and then on Friday we're going to continue with the last pages. Thank you.